I'm joking. I'm joking. Just joking. Okay. Numerical differentiation. So this section will not be on the midterm, right? The midterm is only up to and including optimization. This is kind of the second part of everything, where things actually start to get really interesting. So differentiation, what you guys are going to be getting sick of by the end of the next 2 weeks is Taylor series and basic algebra, to be entirely honest. The name of the game is going to be doing Taylor expansion, right? Taylor is all about differentiation. What we're going to be doing is rearranging that to isolate the terms that we're interested in. And then we're going to apply some tricks to cancel out the ones that we're not. And we're going to try and cancel out some of those higher derivatives. Okay. So we've already kind of started on the idea of differentiation, of forward differentiation through the secant method, right? This was one of the methods for root finding. We started with 2 points, P and Q. We said the line that connects it is called your secant, right? Your secant is the chord that connects 2 points on a curve. As Q approaches P, you achieve the tangent, right? Basic calculus. I guess that would be first year at this point, yeah. So most of these methods, if not all of them, are going to be characterized by your step size. Okay, and your step size is going to be the difference between these 2 points, P and Q. Not surprisingly, what we're going to be doing is looking at the order of convergence. How does your error reduce as your step size gets smaller? What do you do for uneven spacing, et cetera, et cetera, et cetera? That's going to be our name of the game. Yeah. So this whole approach kind of motivates the forward difference formula. And the idea here is that we're going to start off with, so we're going to start off at our point and we're going to look forward, literally forward and then backwards, and then there's going to be a central. We touched on central a little bit when we were talking about, what was it? Subtractive cancellation, I think, but we're going to circle back to that one now. Okay. So what you do is you start off with your Taylor expansion, right? You say that your next point, x plus h is your step size, is equal to f of x, plus f primed f h plus f double primed h squared over 2, right? Vanilla Taylor. Okay. Let's only look at the first few terms. We got that, and then we solve, and lo and behold, this is our forward difference formula, right? This is a first order accurate model because it's only dependent on the first because the error is h squared, right? And here's a nice example. Right, we've got a rocketry equation. We can calculate the analytic acceleration, right? This is for your velocity. We can calculate the analytic acceleration just by taking the derivative. No problem. This is our analytic formula, and then we can use that to kind of poke around and check what happens with the finite difference. So this is our velocity over time. This is our acceleration over time. When we throw the finite difference formula at it, this is forward difference. It's literally f of x plus h minus f of x divided by h, right? And then we do it for h is 2, h is 1, h is 0.1, and what we get is this guy. So our red line here is the analytic formula, right? The blue line is h set to 2, 1, and the green line here is actually lying basically right underneath the red one. Okay? Anybody notice anything funny about this graph? I'm going to give me a qualitative description of this graph. What happens with h? As h gets smaller, the solution gets more accurate, obviously, right? It has to, but it's also monotonically decreasing, right? For large h, it starts high, and as h gets lower and lower, it's going to get better and better and better. Do the exact same thing for backward difference. Now you just flip all the signs, right? H gets replaced by minus h. Boom, boom, boom. You get down to this equation. You do the same thing, and now you get the opposite behavior, right? Red and green are overlapping here. That's as exact as you're going to get within numerical error, right? And you start off with 2, 1, 0, and that has the exact opposite. Whenever you guys have something that looks a bit above, but kind of like well characterized above, and a bit below, but well characterized below, average them. Simple as that. So the idea here is, can we combine effectively the forward difference and the backward difference together to arrive at an even better solution? And of course the answer is yes, right? So you look at the forward and backwards expressions here, and you just subtract them. And all you get is f of x plus h minus x minus h, right? This term cancels out. This term doubles up. So you've got 2 here now. And now you've canceled this guy and actually every alternating power, right? You've canceled your power of h squared, your power of h fourth. So you've got this cubic power and then h to the 5th. Okay? This is the magic. When you go and you evaluate this, you truncate off the h cubed part, right? All you get is this funny guy, which is your central difference formula. The funny thing is that this does not actually have the evaluation at the current point, right? It has that one and it has that one, but it doesn't actually have the point of interest. It's funny. Note also that it's the same number of function calls, right? Functions, when you're doing like NumPy or something, it's like x squared. Okay, that evaluates super fast. If you're doing COMSOL multiphysics and your airfoil optimizer just took, right, like half an hour to converge and half the time it didn't converge, right? Like keeping the number of function evaluations small is key. Very, very key. This is the point behind this stuff. When we look at the central difference, lo and behold, we've got something that's a little too hot, a little too cold, but the small one was just right. Right? So what we can do is we can compare the errors, what happens with this stuff. And what you're going to see is that this is a second order accurate method. Same number of function calls. Okay? This is a forward difference with h is equal to 2. This column is going to be the backward difference with the same and the central difference. Right? And what you get is kind of bad but above, kind of bad but below, much, much better in between. And when you reduce those step sizes in the forward difference, this is order of convergence, right? For the forward difference, the error goes from what, 0.46 to 0.23. And that kind of stays the same throughout the different points, right? So this is a linear order accurate method, H1. You half the step size, you half the error. Make sense? Definitely, like, there's only so much that can go on this midterm, so honestly, like, that's definitely going to go on the midterm, right? Just so you guys are all aware about that one. Okay. Same thing with the backward difference. It displays the exact same behavior, not surprising, right? And the central difference, instead, when you do the same thing from h is equal to 2 to h is equal to 1, all of a sudden you get this order of 4 reduction, which is the big payoff. So, to review, it gives a more accurate solution, same number of function calls, and it becomes more accurate with step size quadratically. So not only is it a better answer, but it gets better faster than the other ones. It does require information. So if you're at this point here, it is going to require information from over here and over here, right, in order to get that. Can you see where that's going to be a problem? You guys have all done, most of you guys have done computational multiphysics at this point. So where is that going to be a problem? Central difference. So say you've got an interval, that's your mesh. If I asked you to find the first derivative at this point, what you would do is calculate f at x minus h over here, right? F at x plus h over here, right? And then you get a very good answer in the middle, right? Okay. Where is that not going to work? At the bounds. Yeah, sorry. In hindsight, I shouldn't have drawn those lines out, right? At the boundaries, you're going to have to do something different. And now you've got a little bit of a problem because at the boundaries, if you do first order, like forward and backwards, that is order h, and now your central difference is order h squared. So guess what your total error for the entire calculation is going to be? What's that? Well, specifically, if you've got part of your problem that is order h accurate, and another part of your problem that order h squared accurate, and you wanted to assess the total accuracy of your method, guess what it's going to be? Chain is only as strong as its weakest link. So what's it going to be? Nope. Yeah. Not going to be h squared, right? So the problem is that I'm actually going to show you an example, but the example contains the solution to this, right? If you have part of your problem that is accurate and another part that's yay accurate, right? Your is just going to introduce all that error. And however accurate the rest of your stuff is, it doesn't really matter because you have that giant source of error over there. So we're going to have to do something else at the beginning and at the end. Does that make sense? Think about it in terms of error propagation, right? If you've got, I don't know, you're measuring your distance in your car, right? And you've got a good accelerometer and you can calculate your acceleration, but you're not sure where you actually started, right? Like no matter how accurate your odometer is, you're still not going to get a good position. That's actually integration, which is different, but yeah. Second order derivatives. Here we go. We can do the exact same approach for second order derivatives. The algebra gets a little bit more complicated because we need a few more terms, but the basic result is going to be the same. Once obtained, here's the magic, we can use the second order approximation to improve the first order approximation, right? So forward difference method is f at x plus h is equal to f at x plus f primed at x h plus f double primed. Sorry, I'm writing sideways here. You guys get what I mean here, right? We canceled off this term because it's a higher order correction. If we have an approximation for this, we can actually use it. It's in the notes, right? You can actually use it to improve that. And guess what? That's going to make it order h squared at both boundaries. That's the solution to the previous problem. Okay? So consider the Taylor expansion. Now we're doubling the step size, right? 2h, blah, 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 blah. Recall the one for a single h step size. And now we subtract it, and we get this nice formula for f double primed. Go through the algebra in your own time. It's pretty basic. Okay? This is a linear, right? Order h linear because of the way that the algebra is shaped out. You could also derive this considering the first derivative of the first derivative, right? If you just did the first derivative at f of x, the first derivative at f of x plus h, and you did the derivative of that, then you could also get the exact same formula. You have to get the same formula. It has to be, there's no more information in there. The nice thing about that one is that it's a recursive definition, right? Which means that you can get into recursion programming and you can do all this, nth order differentiation, right? In a clean way. Is that a question? Good? Okay. So we can now use our approximation of f primed, so we can do this both ways, right? We can revisit the original approximation of f primed and use our approximation for f double primed to improve it. The way it works, and you have to be careful with the h's, right? Because you've got h above, h below, h cubed squared, everything. Take your time with it, right? So we've got f of x plus h, f of x, boom, boom. And now we're going to substitute in our expression in here, right? We calculated what f double primed of x is. It's this guy. Let's plonk it in there. Let's collect our terms. And now we have a new expression for f primed at x that's forward. So we could use it at the boundary here. But now it requires 3 data points. Right? You've got 1, you've got 2, and you've got 3. F of x plus h, f of x plus 2h. But it's better accuracy, which is what we're after. However, notice that this guy is h squared accurate. So it's actually comparable to the central difference. But this guy now requires 3 function calls. Central difference only require 2. Central difference is a quantifiably better algorithm than forward difference. But where you want to use it is on the boundaries. And actually, the NumPy tools, I think it's grad or diff, uses this implicitly. It's smart enough to figure that out. Okay, if you are interested in the nth order forward derivative, feel free to go through this equation. It's one of these complicated ones, but this is the infinite calculability differentiability formula. We can compare the errors. We should be able to compare the errors. Apparently not. Oh, I think my function definition didn't carry through. Okay, well, anyway, the error goes quadratically, right? You half the step size, and it improves the answer by a factor of 4. Backward difference, same thing. You get the same thing, just going backwards. Central difference. You could also do this. We could also get a higher accurate central difference formula by doing the exact same approach as we did before. So what we had was, let's see, if we subtract the forward and backward second order expansions, we get the central difference. And then we can use that to correct the first order. And now we get an order H4 accurate formula for the central difference, right? So if we decrease the step size, we cut it in half. Now it increases by a factor of, 16? Right? Which is good. But the payoff is that now we have to do 4 function evaluations. Typically, okay, so this is just a cute little graphic. Forward is forward, backwards is backwards, central is central. Right? So the accuracy of the approximation can be improved in one of 2 ways. Either decrease the step size or use an approximated higher order derivative. But with the payoff, or excuse me, with the cost, that the more accurate differentiation requires more function calls. As tempting as 2 is, so here's, you know what, I should move this summary later into the thing, but I'll just tell you guys what's going to happen. It's kind of tempting to use like the higher order, like, hey, I'm doing this stuff, I should make it as accurate as possible, right? In general, actually, you don't want to do that. In general, what you want to do is your first option to change your step size. Probably, I'm going to say one of the main reasons you want to do that is because you'll very rarely actually have even grid spacing. All of this matters critically on the even grid spacing. When you have uneven spacing, which is 2 down here, this thing falls apart. So if you have a regular mesh, then you can do this. Typically, again, we've done column cell. What do we do in column cell when we have a boundary? We bring down the element size at that boundary to get higher resolution. That's kind of the more, frankly, engineering approach. That's finite element. It's not finite difference, but finite difference. Actually, no. Finite difference, typically, you would have a regular mesh. There are permutations where you can have unstructured meshes, but they get very complicated very quickly. In general, finite difference methods, you want a regular mesh. Okay, higher dimension. Yeah, this one didn't come through. Apologies for that one. I think I actually have it here. So the funny thing is that these equations render in Colab, which is where I wrote all this stuff, but it's refusing to render in open or GitHub pages. Anyway, so higher dimensions goes trivially, right? Because that gradient can just be done element by element. All you do is you just have to repeat it in the different directions. Of course, what this means is that you get a bit more complicated because now your boundaries are not just a line, it's actually a corner, and you're doing a grid. So you have to be a little bit more sophisticated with that one. We can do funny little plot here, and these arrows came out super small, right? But if you want to do something like the gradient of these things, you can see where the arrows are going there. Any questions on that so far? Okay. So as long as the data is evenly spaced with step size h, whatever it is, we can use finite difference directly and effectively and efficiently, right? Beware the boundaries. Central difference is better quantifiably, right? But you have to be a little bit careful about that one. So as an example, let's find the derivative of a discretized function, right? So this is a function. I'm pretty sure it's a quadratic. Yeah, looks like a parabola. So we have these data points, right? So in general, you would have some y value, right? You have some function. I think I actually have it as x squared, but whatever, right? This looks like a parabola. You won't have these lines, right? What you would have are these open circles at x0, y0, x1, y1, x2, y2, right? All the way over. And then you're just kind of drawing these straight lines as you go, right? And the question is, okay, what is your derivative? So we've got that. Oh, that's late. We can use, this is where the nice part is, right? If you use the NumPy package implementations for gradient, it'll identify the boundaries. So what you do is you give it these lists, right? This is your list of x points. This is your list of corresponding y points. You give it those two things into your gradient, and you calculate it, and it looks like this, right? NumPy's gradient is smart enough to understand when it's at the endpoint here, do forward difference, and it's at the endpoint here, the boundary, and do backward difference over there. This is what you get. If you got a plot like this, would you trust it? I see some shaking heads. Why not? Right? Bearing in mind, just ignore the fact that I just told you that this is a parabola, right? So parabola, obviously, like it's supposed to be a straight line, right? If you saw this plot, why wouldn't you trust this plot? It looks like a zoomed in cubic, but if you use the super effective and I'm looking for something flat here. Doesn't matter. I usually like to just get a sheet of paper and you just put it there. It's actually like right flat across. And if you look at if you actually put on the points here too, you'll see that it's not just like 1 point here and 1 point here. Like, no. Every single point in there is exactly in line. And it's just at the boundaries. Whenever you have a case like that, just as like general advice, whenever you have something that like is behaving one way in the middle and then something screwy is going on at the boundaries, like boundaries, if somewhere is going to fall, it's edge case problems. Your edge cases are going to tell you a lot about your physics, right? If you have something that's like perfectly bang on flat in the middle, screwy at the ends, there's something going wrong at the ends. Who knows what's going on at the ends? I just told you guys so. What was that? Nope. I like the thinking, but nope. No. What does that mean? Oh, I did set the boundaries. Oh, no. I'm not solving anything. I generated a function, and I already told you what that function was, right? The function was a parabola, right? This should be straight. Okay, I'm telling you right now, it should be straight. Why is it not straight? Why is this screwy at the boundaries? Right? And what does that mean? Why is that a problem? Yes, order accuracy, right? If you went through and you resampled all this at a smaller step size, in general, you won't be able to do that, right? Because you're going to be getting your data from some reading or something like that. If you did that, then this is erroneous, right? The fact that this slope is like that and everything else is like that means that there's something screwy going on at that boundary. There's a problem associated with that. This is the difference between h squared accuracy and h accuracy. If you just switch the edge order in the NumPy gradient, what it's going to do is it's going to apply those second order accurate forward and backward different formulas for you automatically, which is really nice, right? If I didn't give you the package, then you would have to do that, right? But because you have the packages, it's one of these double-edged swords, right? Because you have the packages, you can use it, but you're also expected to use it, Right? When you do that, lo and behold, you get the orange line, and all of a sudden it lines up perfectly. Does that make sense? Right? If there's nothing else that you guys take away from honestly, like finite difference is kind of obvious, right? Anybody who knows what difference means can basically do finite difference. Central difference is a little bit of a surprise. They're like, hey, wait a second, I can actually get a better answer, right? Just by doing this trick, but honestly, it's pretty straightforward. The key there is your step size and how things change depending on your step size. Your step size will never be good enough. I'm telling you right now. In very, very few cases will you actually be able to change your step size. And in even fewer cases will you actually be able to get like small enough where this is actually useful, right? In general, because you're going to be using something like column cell, finite difference does still like pop up a whole lot. It's actually going to pop up big and strong in time stepping. That's how we do time stepping, even with finite element method and everything else. It's all through finite difference for the time derivative. Okay, so just keep that in mind. Okay, what's going to be happening with that one? All right. If you have unevenly spaced data, can you still do all the techniques that we just talked about? It won't help you. Feel free to take a look at that. That's not going to help you. Obviously, when the professor asks a question like that, the answer is obviously going to be no. So let me rephrase the question because I'm in like midterm mode, right? Although this is going to be on the midterm, so a bit more of confusion. But which, if any, of the finite difference methods could we use for unevenly spaced data? What's that? Forward, backwards. Which? Yeah. Can't use center. Anybody think you can use center? Okay. Anybody think you can use forward difference? The first variant, right? F of the next one minus f of x. Raise your hand if you think you can use it. Right? Yes, you can use that one. Right? Backward. Yes. Right? If you can do forward, you can do backwards. Central. Why wouldn't you be able to do central? First of all, why could you use forward and backwards? Anybody? I'm going to ask the back corner here because everybody's quiet. Somebody from the back 3 rows. Okay, water bottle in the back corner. Why can you always use? Not just can you use it, but you can always use. Why can you always use forward and backward difference? What's that? Anybody for the steal? I'm going to start moving row by row. Right? But why? Okay, so why does that work for forward and backwards, but not for central? Bingo. That's it exactly, right? It's because the forward and backwards only uses a single step. You only step one way, or you only step the other way. There is no implied constancy of that step going in either direction. And for that fact, forward and backwards works all the time. That's how we can use it in time stepping, right? Time stepping, you're going to have your initial, you're going to predict your next one. You can always use it. Central difference, no. Improved accuracy, right? Next one. Can you do the forward difference method with the improved accuracy? Anybody? Even before that, can we do the forward difference second order derivative? I see some heads yes. Raise your hand if you think you can. For unevenly spaced. Wrong. Sorry. The forward difference second derivative, right? Your second derivative requires 3 data points. And the 3 data points also implies the constancy of the step sizes, right? That's the Taylor part. That's the tricky part, right? Which means also that you can't do the first order higher accuracy one either because that used the other one. Forward and backward difference are the only ones that work. What else can we do? You guys have been answering a lot of questions, so I'm going over here now. Yeah. Shh. 3 of you guys at the corner there. Nobody, everybody's being very quiet here. All right, well, somebody already spoiled it. We can always fit a curve, right? We can always take those data points. We can always fit a curve. If we had 3 data points, what order polynomial could we fit? With 3 data points, you can always fit a quadratic, right? You can always do that. And if you're going to be able to do that, you can just fit your curve and take the derivative, right? And if you do that, kind of the go-to way to do that is to take the Lagrange interpolation. Remember when I said like Lagrange interpolation is one of those things that it kind of like forms the fundamental part of a lot of different algorithms, but few people actually use it directly. This is one of the cases where it actually is like forming the fundamental part of the first derivative. So Lagrange interpolation will give you that parabola. You can just take its derivative, right? And now you've got an expression. If you had 10 data points and you wanted to know the derivative over the entire thing, this is a midterm type question. Would you do something like this? I have 10 data points. I want to know the derivative at every single point there. Would you do something like fitting a curve, fitting a polynomial, and taking a derivative? Do you remember what that one's called? Runge's phenomenon. Runge's phenomenon is going to tank you. It will always tank you. Basically, as soon as you get up past, people are generally speaking afraid of going past cubics, right? As soon as you're past cubic, you're into that, you're into the curse of the high frequency oscillations. Anybody know a practical way to change that, to modify that slightly? Right? Not you. Different question, right? Different person answer that one. So you have 10 data points. Again, this is midterm. This is midterm territory. Okay. You have 10 data points. You don't want to fit a polynomial. You could. You could fit a polynomial to all 10 data points. You could take its derivative and be done. You would be terribly wrong everywhere almost everywhere, actually, because of Runge's phenomenon. What else could you do along the similar flavor? There you go. Cubic splines are stiffer. They will damp out those oscillations, and you will basically get a very good answer, right? Using that approach. Except if you have uncertainty. Right? You can see, if you haven't seen the tie-in between like the differentiation and the curve fitting and the interpolation versus curve fitting, like this is hopefully going to hammer it home for you. Let's introduce a little bit of error. I hope this actually rendered. Yes. Oh, it didn't render at all. Wah, wah. Okay, guys, I'm not sure why this isn't rendering. I'm going to have to do this by hand. All good. If we go back to our rocketry, oh yeah, because it got moved over. So all this stuff was done in Colab, and then I moved it over to GitHub Pages, but I think it broke half the dependencies. So like a lot of this stuff, this is trying to call the rocketry velocity equation, but it's not able to get it because I was in a previous page. Are those better? Yeah, are whiteboard better than chalkboard, generally? Yeah, okay. Thank you. Glad one of us is prepared. Alrighty. When we had our velocity, this was height versus time, right? We could do the finite difference method, and what we would have gotten is an acceleration that looks, you know, something kind of reasonable, right? Nice and smooth. Yeah, it's just smooth line. Here, put. Right? So we've got our velocity, we've got our acceleration, right? No problem. What we do here is we add a little bit of noise to the velocity profile. So the velocity is going to look like this. I'll update this and resend it. So you're going to be looking at this, right? And you're going to be thinking like, this is a pretty, would you guys consider this to be a smooth curve? Like it's pretty smooth, right? Like if you're measuring velocity of a rocket and you get something like that, like you're good. You're good, right? When you calculate the acceleration, it's going to look something like this. Even with evenly spaced data, you're still going to get that gobbledygook. Anybody guess why? Differentiation tends to amplify error. The problem is that when you have two data points that goes like that, say that's the real one, but now you have something that very quickly has gone like that just because of uncertainty, right? Your derivative is now that. And then randomly, your thing is down here, and all of a sudden, your gradient has gone down very quickly. If you think, wait a second, we could throw Fourier at this, like, and if you guys aren't very familiar with Fourier, like honestly get familiar with Fourier because it's horrendously powerful, right? If you throw Fourier at it, and you look at the spectrum, right? If you just have a signal like that, and it's pure, there's no noise associated with it, you're going to get a very clean Fourier spectrum because the period of this behavior, the behavior of this function over space is nice and smooth. With the noise, you're going to get this garbage. And this garbage is your noise. Very short period, right? The amplitude actually doesn't matter so much. It's the frequency. It's the super high frequency. And the differentiation is going to pick up on all that high frequency stuff. And it's just going to destroy your stuff. And it's a little bit insidious, right? Because like you look at this and you think this is smooth, and then you calculate the derivative and it's all over the place. If you ever actually calculate something and it looks like this, like there's something wrong. Nobody hand in an assignment where you tell me that any curve ever looks like that, because it doesn't. You did something wrong there. What can you do about it? First one is pre-filter the stuff, right? What you could do is, so you could actually do, what would this be? A high pass filter, right? Straight from circuits and frequency and signal processing and everything, right? You cut off the noise. That's an option. But say you didn't have Fourier toolbox with you. You could apply a pre-filter. You could just do a moving average, right? What you do is you take this point and you say this point is actually the average of this guy goes something like that. No problem, right? You guys know moving filter, right? Moving average, you take the one behind you, you take the one in front of you, you average those ones, that becomes the one in the middle. This kind of sounds like central difference, doesn't it? Right? What's the other one? Low pass filter, reduce the high frequency noise. You could regularize the derivative. I think this one's called Tykhoff's regularization filter scheme. I don't know. What you do is you require smoothness of the derivative. So when you're calculating this, it requires like a bit more sophisticated algorithm, right? But what you do is you say this derivative has to be somewhat related to the previous one. It can't have this massive thing. And so you're penalizing lack of smoothness. And if you put that in, then it's a way to what are the benefits with that one? You can do it dynamically in a forward sense. When you're doing a moving average, then you kind of have to look before and afterwards. Requiring the regularization, you can actually just say based on the previous one, the next one can't move too much. And this is good for time data, right? Real-time processing. When you have a GPS signal or something coming in, right? Svitsky-Golay is one that the My Thesis Advisor was all over. what you do is you actually have a moving window and you do a best fit low order polynomial, right? Which is a little bit different than the cubic spline. Cubic spline technically means that it's an interpolation algorithm. This is the curve fit equivalent. So what you're going to do is you're going to have a bunch of data points like that, right? And you're just going to do a best fit quadratic. We can do that effectively and reusably because we have those toolboxes with the the companion matrix. We can run that in place. That's your Svirsky-Golay. And in my opinion, the correct answer is we're going to integrate instead. Just like differentiation tended to amplify noise and those high frequency components, integration in a lot of ways is the opposite. In this way, it's going to destroy those, right? Because you're literally going to be taking whatever's in front and adding on whatever's behind for a random noise. Those two things are going to be canceled out. So I'm gonna finish this part by saying that probably the go-to way to do this is instead of taking the derivative just from your data, you would actually integrate it to a higher order and then take the derivative of that cumulative, which is actually usually the better way to do it because you cancel that noise. But we'll come to that one later. Any questions? Excellent. Look at that, I'm even early. 4 minutes early. Okay, you know what? I'm going to use the 4 minutes just to get ahead a little bit here. Hopefully these slides and these equations. Oh, no, it didn't even render the picture. All right. That's what happens when you try and do stuff. Okay. Numerical integration is the opposite, right? Integration, if you remember this picture, yeah. I don't know why like half the stuff isn't... You have a curve, it looks like that, right? The integral is just the area under the curve. We're back to area under the curve, right? Integration tends to damp out experimental noise in contrast with the differentiation, right? Area under the curve is super easy. Here's a nice graphic that isn't rendering for whatever reason. I think it doesn't like SVGs for some reason. Was that? Yeah, I love SVGs otherwise. Yeah. Do you guys know what the difference with SVGs are, by the way? I don't know if you've like seen the final format. So SVGs are scalar vector graphics, right? You can actually, because they are actually using splines. They're all over like cubic splines and everything like that. The nice thing is that you have infinite resolution. You can zoom in as much as you want because it's literally geometric instructions. So I think that's the basis for like all the CVC cutting equipment, 3D printing and everything requires that stuff. If you need tools for that, Inkscape is really, really good. Free software, freeware stuff. It's really nice. For definite integrals, right? So there's definite integrals are where you actually have the boundaries, one side, the other side, as opposed to the indefinite that go on forever. We're going to have approximation methods for that one too. The integration sign looks like an elongated S because it is. Right? It is literally the summation of everything under between it. Yeah, I'm not going to go further actually, right? We're gonna come out with two different approaches based on whether or not we have a function that we can evaluate, f of x, or we have only the data pairs, x and y. Right? We're going to get different methods to take a look at that. Any questions? All right. I see the red border. Screen should be shared. So, Notebook LM. The link is on the cover of the page. These are the flashcards on the right. This is the midterm practice quiz. Right? Feel free to go nuts. What else? Yeah, so the midterm is 25 questions, one question each. It should take you about half an hour or something like that. If it takes longer, that's absolutely fine. You have the full 3 hours to do it. If you do finish on time, then please do come over to the lecture that I'm hosting. I was told to introduce Shahab at around 3:15. So to introduce him. So event opens at 3. introduction at 3:15. I think he's talking for about 45 minutes. But Shahab is a McMaster grad. He went through OPG, worked his way up. Now he's over at OECD NEA in Paris. Tough life living in Paris. And he's the coordinator of the AI expertise group. So he's going to talk about some of the cool stuff that they're doing on kind of the international stage, which is really neat stuff. So I would encourage you jump in on that one. What was the other one? Yeah, okay. I'm going to go through assignment 3 and then I'm going to circle back to this one. So assignment 3, you have 2 circles. What's the first thing you do? If you have anything ever, plot it, right? When you plot it, you see 2 circles. How many points of intersection can have 2? Well, okay, first of all, when we're asking for the roots, what are we asking for geometrically? You know this from the lines. This is the extension of the lines, right? The solution of a linear system is, right? You plot out each row as a line, and what do you get? Intersection, right? No more answers for you. Now it's over to them. Got to spread the load here, right? When you're doing it, and it generalizes precisely. Okay, so when you're asking for the root of a more complicated nonlinear system, you're still asking for the points of intersection. That's what this is. That's what this is all about. Okay, so given that you have 2 circles, how many roots could there be? You got it, right? And you can see that super, super quick just by looking at this thing, right? Let's see. So you write out f of x. This is easy. You just move all the constants onto the left-hand side. Write out the Jacobian. Practice your differential equations a little bit. Not differential equations, derivatives. And then write out the Newton-Raphson method, right? And this one, I asked you to actually program it just because I want to hammer it home where the linear system is coming in on this, because Newton-Raphson is frankly all over the place, right? So you've got 2 functions, circle 1, circle 2. You generate your linear space for plotting. This is the plotting one, right? Looks fine. You define your total function. So this is a vector function with vector input, right? You define your Jacobian. Again, with Jacobian, if you want to get really fancy, or depending on how Gemini felt that morning, it might have popped it over to SciPy. SymPy. SymPy is the symbolic logic branch of Python, and then it could do all this stuff automatically, which is convenient for a lot of cases. But the simplification algorithms in SymPy are kind of lackluster compared to something like COMSOL. But anyway, Newton-Raphson, right? So you give it your initial guess, and then you enter your loop. You set your Jacobian, right? And then you do your linear solve. And this is the magic. This is where all the magic happens. Everything goes in there. Is this a dense linear system or a sparse one? Anybody? Class? Anybody? Gonna go up here. Group of 4 people here, 5 including Bowen. How do you know if this is the dense linear system? First of all, what am I asking about? You should know this for the midterm, guys. So if you know it, then shout it out here. Nobody? Red hat? Orange? Not gold. Which part am I talking about when I'm saying sparse? Sparse or dense linear system. I'm talking about the begins with an M, ends with a matrix. Right? So the matrix here is Jacobian, right? And if you look at the Jacobian, right, you can try and read it off here, or you just go back to your previous answer. Like it's completely filled. So this is a dense linear system, right? Now it is 2 by 2. Can 2 by 2 ever really be dense or sparse? But technically this would be considered a dense linear system. A lot of these root finders will be, frankly, which is a bit of a downfall to these types of methods. It's not easy to make these things sparse. That's just the way it is. Okay, so you solve, you increment, you return your x, and off you go. And you have to repeat that how many times? 3 people in the row here. I'm going to choose somebody. Tim Hortons. You already got it. Twice, right? Why twice? Because it's 2 roots. Because you've got 2 points of intersection. You could repeat it as many times as you want, but you know going into that it's 2. Okay. Question 2. You've got the wire, you've got the charge. I give you the equation, ask you to, which one did I ask you to? Yeah, find the R that minimizes T. Okay, so this is a practical engineering one. You could have used whatever optimization method you wanted to get to the solution. The magic here is what are some of the things that you guys encountered when you were going into this thing? Because I just gave you the entire optimization toolbox. Okay, so this time I want to hear a voice from over here. Somebody shout something out. What method did you use? What did you have to give it? I'm going to start calling on people. Black water bottle. You already answered one. Derivative. What's the problem with the derivative method? You got it, right? It's okay if you have symbolic logic, right? You can just ask. I would be careful asking Gemini what the derivative of that equation is. Because Gemini is AI in general, in my experience, is not so good with the arithmetic part, and like differentiation is very arithmetic, right? Wolfram Alpha is a super easy one. Wolfram proper is fine. Maple is fine. Any of these tools can just chunk through this super quick. Okay, so if you didn't want to use derivative, by the way, what's the benefit of derivative? This is part of the midterm review here, guys. What's the benefit of derivative-based optimizers? Ah, come on. Okay, what did you use? That's okay, too. Brent's method? Okay. Yep. Why? Yeah. Yep. Yes. Yeah. Perfect. Perfect. Okay. Somebody else. Why would you use a gradient method instead of Brent's method? I'm going to start poking on people. Black lunch bag. Ooh. Tricky. Tricky. You want to jump in? Both will give you an approximately equally bad answer. Both will give you a good enough answer because both are tolerance based. Yeah. So, is gradient based methods less or more computationally intensive than the direct methods, of which Brent's algorithm is an example? Guys, midterm, come on. Not a midterm in like what, 4 days, 3 days, something? Come on. Anybody for the steal? And let's start naming people again. Okay, we're going to move over to the right there. Silver laptop, Dell. How do you mean? Which one? Yeah. It's tricky. It's tricky to say which one is more computationally intensive because it takes more iterations, right? The gradient-based methods they're getting more information at every step, right? That's the name of the game. So at every single step, you're calculating your value, you're calculating your gradient, you have more information, so you're going to need less steps, which makes sense. But on the other hand, when you have the gradient of a vector function is going to be a matrix, and now you need to solve a linear system. Right? And is that more or less computationally intensive? Depends on the linear system. Depends how nicely it converges. Is it well conditioned, et cetera, et cetera, et cetera. Right? So it's not actually so easy to say which one is more computationally efficient. Typically, people do go for, okay, so when would people go for gradient methods versus direct methods? And vice versa. The opposite is also true. Back at the back. Ah, come on, man. All right, moving on up. Clarissa, when would people go for direct methods versus gradient? Also fine. Okay. Consider what COMSOL does. It's a little bit of a cheating question because you don't know the magic. But what do you think COMSOL is doing? And take a guess. COMSOL is doing the gradient-based method. Higher dimensional functions. So there's Brent's method. This one is kind of an easy one because it's 1D. And 1D optimization is frankly trivial. You could throw whatever method you want at it, and it's going to stick to the wall. It's going to be fine. Brent is very nice for that. But the problem with direct methods is that you have to sample all over your space in order to guess and like to bracket and kind of track that problem. Consider the amoeba method, right? You're moving kind of this high dimensional simplex through your space. And for 1D, that's fine because that's an interval. When you're doing COMSOL and you have 100,000 degrees of freedom, that is a 100,000 or it's a 100,000 dimension problem, and your simplex goes like that. So with Newton's method, maybe you need 3 or 4 Newton iterations to find your root. If you were going to throw something like the simplex, Brent wouldn't work because that's 1D. If you were going to throw the simplex method at it, it would take on the order of hundreds of thousands of iterations. You wouldn't need to solve your linear system every time, but it would still take like a massive, massive amount of these things. And it doesn't even parallelize very well. It could a little bit, depending on how intelligent you want to be. Does that make sense? This is turned into part of the midterm review too. Any question? There isn't. Doesn't exist. Correct. Yeah. Brent is particularly useful for 1D problems. And it's kind of the go-to for 1D. Yeah. Nope. More just kind of depends on how much the user wants to do. Because if you do need to calculate the derivative, again, I wouldn't have trusted Gemini to solve. Did anybody ask Gemini to give the derivative, or did it like calculate it by itself or something, or did it just throw like a direct method at it? Yeah, doesn't matter. If you feel adventurous and you want to calculate the gradient, or you trust Gemini enough to do that, you can, and it'll do it faster. But honestly, the default go-to in this one is usually the amoeba method, the Needler-Mead, because that one is going to take a whole bunch of iterations. But especially for small problems like this, it's a difference between like a microsecond and 3 microseconds, to be honest. Do you guys know offhand when you would have to use a gradient-based method? I don't think this question is on midterm. I considered it a bit beyond midterm, but maybe future years won't be so lucky. The gradient-based methods will find saddle points, because the gradient-based methods are looking for roots of the first derivative, which are minima, maxima, and saddle points. So that's the other reason why a lot of like the big codes for the bigger problems, when you get into like equality constrained problems, which is pervasive, which is all over the place, right? Then you need the gradient-based methods, because those will find your saddle points, and that's exactly what you need for the equality-based constraints. Anybody else? Okay. The other magic here was if you were using a bracketed method, you had to understand that R had to be greater than A, right? It had to be greater than A. You probably want to set it less than, I don't know, something outrageous, 2A or something like that. And if the answer came out to exactly 2A, then you know you've done something wrong. Increase the range, like change according to that one, right? Okay. Question 3. Given the data in columns, this is an exploration of curve fit. curve fit I wanted to dwell on a little bit because you're going to be doing it. It's pretty straightforward. You have to give it the function in terms of your independent coordinate, your temperature, and your parameters, and then you tell it, find the optimal set of parameters. What is funny about Arrhenius? This was my answer, by the way. What is funny about Arrhenius? Arrhenius is also one of those things, like if you're staying in engineering and physics and general chemistry, Arrhenius is all over the place, but there's a big problem with Arrhenius. Nobody pick up on it? The exponential is going to cause you grief. Because what that means is, oops, the sensitivity of your result is going to depend very highly on E and not so highly on A and B. There's a weighting problem. And to be entirely frank, there is not a great way to deal with that. You could deal even with the freedom of assigning weights and stuff like that. It doesn't come out as clean. Anybody find the alternative method to solving this? Instead of just trying to solve this equation itself. Did anybody come up with the alternative? You were probably doing it a couple of years ago. Take the ln of both sides, right? The classic experimental analysis, you do a ln plot or a ln plot, you fit a straight line and that becomes your curve. If you do that, then you are boosting the sensitivity of the result to your exponential at the expense of A plus BT. So it kind of depends on what you want to get out of that one. Okay, both are acceptable. Both are absolutely fine. Any questions on assignment 3? All right. Numerical integration. Okay, let's jump into Newton-Cotes. All right, Newton-Cotes are kind of so I kind of like this numerical integration. First of all, it's really useful, but also this is a great example of like the engineer solution, the physicist solution, and the mathematician solution. Newton-Cotes is the engineering solution, right? And the idea is we have some curve. We're looking to integrate it. So what do? We do the same thing that we've been doing for, when did you guys learn calculus? Was it first year? Or was that in high school still? First year? High school? Okay. Back in my day, we had grade 13, so we did it then. No, seriously. Okay, so the whole idea is you take your curve, you take blocks, right? You take your rectangles, and you subdivide, and then sum. Is this the way you guys learn calculus? Right? So it should seem really familiar. Okay. Note that since we're doing summation, you can tell I didn't have my coffee this morning. Since we're doing summation over subdomains, there's no obvious reason why these should be continuous. Right? We've been talking a lot about continuity and smoothness with our approximations. Newton-Cotes doesn't have to be. It's not actually a problem. What that means is that you can parallelize it pretty well. So again, when you move on to multi-core systems, high-performance computing, you can spread it out, and that becomes a whole lot nicer. And it's also kind of a trivial formula, right? Like you do one side, you guys do the other side, everything adds together afterwards. I keep mentioning this, that it comes back to recursive programming. Did you guys do recursion in computer science and stuff? Like, did you guys cover that one at all? In high school? Yeah. I'm not surprised. If you ever get into computer science proper and you end up doing a lot of these codings, recursion is nice because what it means is whatever you do for the whole domain, you can just say, okay, repeat that on the subdomain. Repeat that on the subdomain. Repeat that on the subdomain. And it makes your codes super precise, super clean. They're like 3-line codes that solve everything. And it's massive. It's super nice. That's why I keep dwelling on that one. Okay. Error analysis. As the step size h goes to 0, the number of boxes goes to infinity, and the approximation becomes the analytically exact integral, right? Easy. The order of convergence for integration is also related to the step size, and different algorithms will converge to the exact integral at different rates. Okay, so we're going to characterize the orders the same way that we always have, always this OH notation, right? But now we have to consider the order of convergence in the error on two different parts. First of all is the subdomain itself, because we're dividing and conquering, right? First one is the integral error over the entire block. But then when we subdivide it, we also have to add that up however many times. Does that make sense? So it's because we're dividing and conquering, the total error is the sum. It typically works out to be h, right? Because as your step size gets smaller, you need more and more of these subdomains. So whatever interval, whatever error gets on those small subdomains, wow. Okay, small subdomains gets multiplied by however many subdomains you have. Hopefully I'll become clear in a minute. Data points are typically equally spaced, and that has big payoff on the error analysis on both levels, both on the local and the global level. Yeah, that's fine. You could also run into the situation where you might have sections of equally spaced and then followed by another section of not equally spaced, or even just different equally spaced. So if you're doing like an experimental apparatus and you know something's happening because there's a transient in your reactor core and you bump it down to 1 second timings, right? You get a whole bunch of data and then you're in the steady state and you only need like hourly or something like that, right? Typically what you're going to do is you're going to do 2 of these guys on each equally spaced parts and then put them together, and that's going to be your best answer. Okay. There is a little bit of a funny business that you have to be aware of, which is in some cases, you're going to be asked to integrate over tabulated data. So if you're running an experiment, you don't know what the function actually is. You just have a set of x, y's, right? And you might be asked to integrate over that. Or you have a callable function itself, right? And you can say, what is f of boom? What is f of other boom? An example of a callable function might be something like COMSOL, right? The entirety of the finite element method could be an input, a callable function into one of these integration functions. It doesn't have to be something simple. Riemann integrals. Okay, so Newton-Cotes method is basically you subdivide your system, you approximate that subdivision with some low order polynomial, and then you integrate exactly. Because you can always integrate a polynomial exactly, right? Right. I see all those nodding heads. Okay, Riemann's integrals are polynomials of degree 0, i.e. they are constant, right? Variants do exist for function values at the left limit, middle, and right, and we're going to see why that's important. So the way you do that is, so there's the left Riemann integral. Did you guys touch on this in calculus? Left, right? Yeah, okay, good. So I'm gonna skim through this one, right? So where do you take that constant? Do you take it on the left? That's your left Riemann integral. Blah, 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 blah. It looks like this. If you do it on the right, yada, 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 it looks like this. If you look at the error, so the exact answer to this is 333, right? Left is lower, right is higher, but that depends on the curvature. If you don't remember last lecture, as long as you have something that's a little bit too hot and something that's a little bit too cold, you average them together and it's just right. Right? There was a reason to the 3 little bears. To analyze the error, we do Taylor expansions. I warned you, Taylor expansions are going to be all over this for the rest of like the semester. Taylor expansions through the wazoo. Oh, I forgot to mention about dual numbers. Okay. Okay. So what you have to do is you just write out your Taylor expression, right? You do your integral and you separate out, because since the integration distributes, it becomes really easy to identify where that step size is. That delta x dx becomes your step size, and then you get an equation that shows that the order is on the order of h squared. Okay, I'm running a little bit low on time, and I want to talk about dual numbers at the end there. So I'm just going to refer to the notes for the algebra. Okay, so on each subinterval, the left integral is order h squared. But if we have small intervals, but 10 of them, right? So say our limits of the global integral is from a to b, right? That's our indefinite integral. When we make the subdomain smaller, the answer is going to get better on that subdomain, but now we're going to have more of them. How many more turns into also a factor of h, right? The smaller your step size, the more of these intervals and the more compounding of this error you're going to get. So the error for the global system is typically h times the local error for Newton-Cotes. That's all it ever is. So what that means is that the overall error for the entire integral is actually order h, not order h squared. Order h squared is only on the small integral. Does that make sense? Kinda? It becomes a little bit of a balancing act, right? Because if this is your total integral, right? This is from a to b, right? If you just take this entire thing as a single subdomain, you could do it. It would be a bad answer, but you could actually do it. If you want a whole lot of subdomains, that's fine, right? But now each one of these is going to be a better approximation, but now you're going to have to sum it. And how many of these summation intervals you have is going to be related to your step size h. So typically, if this is order h squared, when you sum over all these guys, it's going to turn into order h. Okay, but there are better methods. Remember, you have something that's always too bad and too bad on the other side, so we average it and to the midpoint. This one, what we're going to try and do is we're going to say, let's find it instead of the left or the right, we're going to find it in the midpoint of the interval and use that, right? We chunk through this thing and lo and behold, we get a better answer. This actually turns into, where's my error analysis here? Okay, I'm going to come back to this one. The error analysis is a little bit more involved. You need to substitute out a few things, but what you end up finding is that it turns into a local accuracy for the individual subdomains of order h cubed, and the sum overall of that turns into order h squared. So this is a quantifiably better one. There is a problem though, because typically what you would have in here is you have data points at 0, 1, 2, 3, 4, blah, 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 right? And you're just asked for the integral between here and here. If you don't have a callable function, that's all the data points you have. So can you actually treat these guys as the midpoint? It makes sense to say that this is left or this is right, right? But if you were doing the midpoint, where exactly is that midpoint, and do you actually have data at that midpoint? Because if you put the midpoint over right on the boundary, then you've got half of the interval that you're not actually caring about. Does that make sense? It's kind of important for midpoint rules. So this guy, if you were using that as left, that would be that. If you were using this, the right method, and you had this data point, that would be that way, right? But you don't actually have the midpoint data. If you did just apply the midpoint rule directly to this, then you wouldn't be doing the same subinterval. You would just be you would have this overhang. And that overhang isn't actually what you were asked for at all. So midpoint is great. If you have a callable function, there are better ones for callable anyway. Trapezoid rule. Trapezoid rule is the first order Newton-Cotes. It connects with a line, order 1 polynomial, right? And all you do is you go from one point to another point. This does make it continuous, right? Because you're connecting the dots, you're literally connecting the dots, right? The formula is here. Running a bit low on time again. What you're going to find is that it's order h cubed on the local one, right? Again, it's a bit more involved how you find that. I'm not going to ask you guys to calculate like the h from these algorithms on the midterm, or I don't think they're on any of the assignments either. So if you're interested, by all means, follow through this. But to be entirely honest, there's not a whole lot of value that I can give you to going through all this stuff. So the algebra is there, the symbolic logic is there. It's all robust. It's all correct. Go for it if you want. But let's move on with some of the practical sides. Okay, so trapezoid is order h cubed on the intervals. The total is order h squared over the whole thing, which is comparable to the midpoint. But trapezoid doesn't have this midpoint problem. So the same curve here, it can just use this data and this data. You connect the dot between them. You calculate what the volume is, what the area is underneath, and then you just sum those. Okay, so this is the an example of solving if integrating sine of x. So this is a callable function between 0 and pi using the midpoint and trapezoid rules. If you look through here, right, what we're going to do is we're going to generate data for the trapezoid rule on like 0, 0.1, 0.2, 0.3, whatever, right? For the midpoint rule, we have to do something more complicated. We have to actually generate it at the midpoint of those intervals and use that. If you didn't have a callable function, you would be SOL, right? Because you can't really use that. So trapezoid rule is generally considered better and an easier application, even though it has similar orders of convergence. But for sine, which is a pretty simple one, it actually performs worse, right? So the exact answer is 2. And the error for midpoint, right, goes down faster than the trapezoid rule. No, sorry, it doesn't go down faster. The error for midpoint is less than the error for trapezoid. What does that mean in terms of order of convergence? If I just give you this line at the bottom here, what does that mean for order of convergence? Which one is better? Midpoint gives you a lower error. Does that say anything about the order of convergence? Faster is the key word, right? So the order comes in from the reduction between the error on these guys, which is roughly an order of 4, factor of 4. Similarly over here, right? It's important when you remember, again, midterm, right? The order of convergence, the order of error is all talking about the rate of decrease, not the actual one. Why is that relevant? Because you could always run this again, frankly, right? And if you only had like tabulated data and it was for like some super important discovery or something, you would probably be looking at this data and trying to fit some kind of curve to it anyway. And then you could just integrate based on that thing. You would have some noise in the signal and stuff like that. But trapezoid is usually the go-to anyway, because it doesn't have this endpoint problem, because it doesn't have the overhang at the end of the domain there. Any questions on trapezoid? Okay. I can actually make a Simpsons reference because the bloody show is still on. Yeah. I can't believe that show is still going. Holy hell. Okay. The Simpsons. Continuing the polynomial degree, right? I told you this was the engineering approximation, right? We arrive at Newton-Cotes order 2, which is, not surprisingly, a quadratic. How many points do you need to fit a quadratic, right? What we can do is we can envision 2 of these subdomains back to back. So we're creating sets of subdomains, and this is how we're going to analyze this thing. It is the conceptualization. There's nothing magic about it. There's no importance to the fact that this one would be some continuous in the curve. This one would also be C0 continuous, but not C1, because you would have that cusp there. Doesn't mean anything, not relevant. In this particular one, because we're considering pairs, we're going to need an even number of data intervals, right? If we have an odd number, then we're going to use the variant, which is the one below Simpson's 3/8 rule. Okay, so the idea is we have these data points. We're going to fit a parabola to it, and then we're going to integrate the parabola exactly. The way that we're going to fit a parabola is back to Lagrange polynomials, right? We're just going to keep using those. They're fundamental to everything. By all means, look back in the notes, but here it is anyway. And this one didn't come out, but the nice thing is that you can integrate this directly. So you can integrate the Lagrange interpolation polynomial before you even provide its data points, which is super nice because now you just have a formula for the integral and what you get is this guy. Feel free to go through the math if you want. Note that you have this factor of h over 3. 1 over 3 is what gives the method its name. This is where the Simpson's 1/3 rule is. 1 over 3 here times h. When you look at the error analysis again, it gets a little bit more involved, but there's some magic that starts to happen here. Yeah, okay. It gets fairly involved. But for reasons that are in here, feel free to look at it. There's symmetries that start to apply. Because you've got two intervals back to back, and you've got a parabola that's centered at the middle point there, right, between those two intervals, you have a symmetry between either side. And that symmetry ends up canceling out one of your higher order derivatives in your Taylor expansion. So Riemann integrals are local order 2, global order 1, right? Trapezoid rule is local order 3, global order 2. Simpson's rules actually turn out to jump one. They skip one. So they go up to order 5 locally and order 4 globally. And that's because you have this symmetry that ends up canceling out. So you get a benefit for nothing, basically, which is attractive. That's what makes Simpson's rules basically the go-to. When you're doing this sort of stuff, that's what you want, but there's a caveat. Here's the example. So we're tacking on to the trapezoid, midpoint, Simpson's error, and Simpson's error just plummets, right? It's order 4, so it goes down by a factor of 16 every time, which is fantastic. The 3/8 rule, what you have to do is you have to fit a cubic to the case. So if you have an odd number of data intervals, then you're not going to be able to find pairs. You're going to have one left over, which is 3 intervals together. So you fit a cubic to that, integrate that exactly, right? And this is what you get. And it actually has a similar accuracy, which is super nice. Again, everything's tied up together. Where's my summary? I forgot to add it to the table of contents. Okay, give me a second, and then I'll let you guys go. All right, giving you behind the scenes peek here. Okay, so this is, I need to add this to the table of contents I was working on yesterday. Okay, Newton-Cotes, especially Simpson's rule, is the go-to for integration when the function is smooth-ish, right? I.e. locally quadratic. If you have uneven data, this entire framework falls flat on its face. It's all based on the Taylor expansion, which requires the same step between each data point. If you don't have the same step, you have to fall back to, there was the question, what is the analogy with the finite difference? You have to fall back to your most basic one. In this case, it's the trapezoid rule. So in the case of completely random steps, you're just throwing trapezoid at it and walking away. And that's actually basically the go-to in general for all cases. For smooth-ish functions, you have other tools that we'll talk about tomorrow. Okay, multi-dimensions, this actually works super easy because the integral is the integral of integrals, right? So you can call this as a recursive problem, and it just goes through all this stuff super easy. Don't really need to dwell on it. Here's just a nice little funky table. For the final exam, you might consider like putting this table onto your cheat sheet. Yeah, I would say this would be cheat sheet material, putting down this table here. I don't recall offhand if I actually have questions asking about like Simpson's 1/3 rule, what is the order of accuracy or something like that. But okay, any questions on Newton-Cotes methods? Okay, before we go, I was remiss in not mentioning last Tuesday about finite difference. I wanted to talk about something called dual numbers. And dual numbers are one of these things that honestly should not exist, but they do anyway. This is how like neural nets are trained using gradient-based methods. They don't use, because you need the gradient-based method. You need the derivative in order to get that. Do you really want to be throwing something like finite difference at something like a neural net? No, because then you need to sample your points. Instead of doing that, they use something called dual numbers. I don't have time to get into dual numbers, and to be honest, I've never seen an undergrad course that even deals with these things. So if anybody wants to do dual numbers for their independent design project, I would be very much appreciated. And ideally, we would just slot that into the course for next year. So write it out on like a Google Colab or something, show off how it works. It's insane. This thing shouldn't work, but it works anyway. Weird. It's just weird. Okay, good. See you guys tomorrow. Okay, guys, let's get started. So what? Yeah, so midterm coming up on Monday, 2:30. If you're done by 3:15, please do come up to Shahab's lecture. It promises to be kind of interesting. Details, I think, are on the MS Teams, one. So, oh, sorry, 1 second. Just need to check something. Forgot to do it before. Yeah, okay. Tuesday's lecture, I'm in a conference downtown Toronto, so I'm just going to pre-record it. I'll just put it up on the YouTube. I'll send it out on A2L, so don't bother showing up here unless you really want to, because it is a pretty cool room at 8:30 on a Tuesday morning, right? But otherwise, you can just watch it on YouTube. No problem. Let's see. For practice problems for the midterm, if you weren't here yesterday because of the circuits midterm, probably the best tool that I can recommend for that is going to be the Notebook LM and the quiz section on there. So it is built up. Have you guys tried that yet? Have you poked at it? Yeah. It's pretty useful, and like it can just keep drilling you. It'll give you the hints. It'll show you the correct answers. It has the links to the references and stuff like that. Honestly, if you spend some time on that, chances are you're going to hit like 60 or 70% of the multiple choice questions that I was able to come up with separately, because there's only so many multiple choice questions you can actually ask on this thing. Let's see. Any questions about that? We should have a bit of time at the end of class today if you have any questions or review or anything. All right. Also, it's a small group, so you guys actually came out on Friday morning, so you guys can get the benefit. Okay. So we're talking this week about differentiation and integration. The last couple of days have been about integration. As I said, there are kind of like the three flavors of it. We did the engineering one, which is Newton-Cotes, which is basically for every interval, you're going to fit a low order polynomial, which you can integrate exactly, right? There's a 0th order, which is your Riemann sums. There's a 1st order, which is your trapezoid rule, which is kind of the fallback for any kind of uneven data spacing, right? Because you can always throw the trapezoid rule at it, and it's actually performs pretty well. It's quadratic convergence to the answer. If you have even spacing or you have regions of evenly spaced data, then you can throw the Simpson's rules at it, but you have to be a little bit careful about the even and odd one. Good news is all that is very easily automated and algorithmed. So all that's already in NumPy, SciPy, and their integration toolboxes. The idea with the Newton-Cotes is basically to look at the Taylor expansion. This is the engineering approach, right? The engineering approach is that you look at the Taylor expansion and you say that if I want a better answer, I'm just going to take higher derivatives, right? You approximate those higher derivatives, you slam them all together, you do your integration formula, and off you go, and you get a better answer. Romberg's rule is actually kind of cool. This is what I would describe as the physicist's answer, and then Gaussian quadrature is going to be the mathematician answer. Romberg's rule is an alternative to Newton-Cotes. And the idea is that you're going to take an interval and you're going to sample it successively at smaller and smaller step sizes. So you can imagine the entire interval to be one step, and then you subdivide that, and now you do it in 2 parts. And then you subdivide that, and now you do it in 4 parts, right? The subdivision by 2 technically isn't necessary, but it makes the math and the procedure a whole lot simpler to conceptualize. The magic is that we're going to use the difference between successive approximations to approximate the error itself and then eliminate it, which is kind of wacky to think about, but honestly, this is kind of cool that this stuff actually works. Okay, to begin with, Richardson extrapolation. Kind of funny that I start off with Romberg's rule and then originally
already jump into Richardson extrapolation. Okay. The idea is that we're going to use successive applications of the trapezoid rule. Remember, trapezoid rule is order h squared for the entire interval. Order h cubed for the individual intervals, but then you have to sum all the intervals, so it becomes order h squared for the totality. Nice thing is that we're going to get a big payoff for doing this stuff. Okay, so the exact integral can always be expressed as your I is your exact, right? And this is going to be equal to whatever your approximation, which is going to be some function of your step size h plus your error, right? This is literally the truth is your approximation plus the error. It looks a bit of a funny way to write that, okay? The associated error EH, we know that EH is proportional to h squared for trapezoid rule. We promised that, we found that out last time. In fact, if you go back into that, you know how I say with order notation, big O notation, you just kind of ignore everything in front of it? If we don't, we go back and we find that it's actually proportional to the second derivative of f times h squared, okay? Keep that in your mind for a second. Now what we're going to do is we're going to take the same interval. We sampled it once with step h. Now we're going to resample it with step h squared. And if we assume f double prime doesn't change much, I'm going to come back to that assumption, then the exact integral has to stay the same. Right? Because the truth is the truth. The truth doesn't care about, the actual integral doesn't care about your sampling frequency, right? Your sampling frequency comes into the approximation. So you say I is equal to I, and you move your terms around and you get this guy. Does this make sense? Yeah. Seeing some confused faces here. Ah, last time. Say we have two sampling step sizes, right? H1 and H2. We know I is equal to, what did I call this? I prime. H1 plus, can you guys see this, or is that whiteboard better? Whiteboard? All right. So in general, I is your approximate as some function of your step size plus your error, which is also some function of your step size. So we're going to do this twice for the full domain. We're going to use step size h1, I primed of h1 plus e h1, and we're going to repeat that. And now we're going to find make sense? Right? All we've done is just replace it by a second step size. Because we know that E goes like F double primed H squared. And we're assuming that this one is kind of the same thing. Right? We can just find out what this ratio is. You just take the error at H1 divided by the error H2, and this comes out to this. If F double primed wasn't the same, then it would still be lingering out here. Then there would be some kind of factor there. But let's pretend it is the same. Okay? Now we say, wait a second, the exact integral, the analytic integral of this function hasn't changed, right? Because nature hasn't actually changed. So you put them together, right? You substitute in this guy, and you do some number crunching. Okay, so what we've done here is we've expressed the error associated with step H2 in terms of the approximations for the other ones, for H1 and H2. And then we're going to insert it back into this guy. And when we do that, we're going to get something that looks like that. Rearrange it. And we get this. This is for this case where h1 is equal to 2h2. So we're subdividing, right? Subdivision is kind of a natural way to do it because it, again, lends itself to recursive algebra. You don't have to do it, but it makes the math simple. When you do that, you get this guy, and this guy is actually canceled off. Here's the magic. This error is this guy. So what is it? Error of the trapezoid rule goes like blah, blah, h squared plus something, something, h to the fourth. You've actually canceled out this h squared here part because you've done this excessive approximation, this excessive calculation. You end up killing that part, and all you're left with is an order h fourth accurate algorithm, which is really neat. Because if, for example, you have data, say you have tabulated data, right? If you have a callable function, you can just evaluate this wherever you want. That's something else. But say you had tabulated data that looked like 3 data points. Okay, so you have x0, x1, x2. These are evenly spaced. I'm just bad at drawing. Right? Newton-Cotes would say, consider this to be one interval. Fit, oh no, this is my curve, right? Fit a polynomial here, right? It could be a constant, it could be a trapezoid, it could be a quadratic, depending on how you want to do it. Okay, it wouldn't be quadratic, you would have to do the other one, right? And then you do another one here, and you add them together. And that, if you did that with the trapezoid rule, you're only going to get h squared for the total integral over the entire thing. Right? So, okay, if that doesn't make sense to you, go back to the trapezoid rule. But with Richardson iteration, let alone Romberg's rule, right? What you can do is you can say, take this data, take step 1 as this guy, right? Step 2 is this guy and this guy. You haven't changed the amount of data in your problem, but you've ended up with a 4th order accurate integral, which is frankly magical. Questions about Richardson? Cool. On to Romberg's. You can repeat this. There is absolutely no reason why you can't subdivide this further. You could take it to, say you had this much data, say you had this much data, right? And there's some algorithm, there's some heuristics involved because it needs to be a power of 2 in order to get it, so on and so forth, to cascade it down, right? You can see how the algorithm would feed in there, but you are going to get basically arbitrary accuracy. And that's something that, like, honestly, you don't encounter very much in numerical methods, that you can get it as good as, like, the computer running is able to do it. What ends up happening is that you have to keep track of your original integrations, the original approximations, and then use them to cancel out the higher order error, improving your answer and improving and improving. You can get down to the general formula here. This isn't the sort of thing that I would ever ask you to, like, memorize and, like, write down on a midterm or a final exam or anything, because honestly, Wikipedia, and this is all integrated in SciPy anyway. SciPy has Romberg. Right, so I think on the on assignment 4, I think there is a question where you'll have to use Romberg. It's in SciPy. Go for it. Absolutely fine with that. Okay, so the nice properties of Romberg is that it lends itself to recursive programming. So as I mentioned last class, if you guys haven't done recursion in programming, it's a bit of a mind twist to get it, but once you get it, the code that comes out is very, very beautiful, very easy to maintain and keep track of. It parallelizes very easily because what you have to do is do, it's integration. And integration is summative between the intervals, so you can do this over and over and over again. If you keep to this rule that H2 is roughly half of H1, this factor of 2, you end up being able to reuse a lot of your data points, right? So even just the data points that you have here, you can use in all of your different calculations. You just keep track of them and then you use them again and again and again. Makes it very elegant. It's integratable to an arbitrary accuracy. And I already mentioned that last one there. However, because we have said that the error is proportional to the step size squared times the second derivative. If f double prime changes dramatically between those three samples, right? It's gonna start playing games with Romberg. So an example is actually this one. Actually, this one isn't so bad, right? Say this is our data. Say it looks something like this. Everybody see that? Right? So say it looks something like that. If you just took this guy and this guy, right? You applied your trapezoid rule, it would look something like that, which is okay. But now when you do the subdivision, this curvature here is going to be very different than this curvature. And it's actually going to be a completely different sign than the curvature of this guy, which is going to break this second derivative, the equality of the second derivative, right? Which is what we had to use to get to this equation when we canceled it out. It doesn't cancel out exactly. The errors, the error properties are still there, but the second derivative doesn't cancel out, in which case it doesn't make it as effective. So not only do you need a structured sampling grid, preferably in order of 2, right? Factors of 2. No, yeah, powers of 2. There's the word. But if your curve is very, has these high order oscillations, then this can sort of play games. And where would you get high order oscillations? Signal analysis. Error, right? Your error is going to be doing something like this all over your entire domain. And that's going to play games. It's just going to play games with you. And this is why, even though Romberg has all these nice principles, right? Arbitrary accuracy and everything like that, putting it back into Newton-Cotes is usually the most robust way to do it. Let's give an example, right? Let's approximate 0 to pi sine x using Romberg rule compared to Simpson's 1/3 rule. We can do this analytically. So what this table is showing, so if you look down here, this is the Romberg rule with 4 intervals. I'll come back to this tableau in a second. This is the Romberg rule with 4 intervals. This is the same with 4 intervals for Simpson's, right? And what you're going to see is that 8 intervals, the error is just going to fall completely through the floor. Simpson's rule is doing very well, but it can't keep up compared to Romberg rule. It's just much better. Down here at 128 intervals, Simpson's rule still has some kind of error that's trackable. Here it says 0. Have we found the exact answer? What have we found? This is on the midterm, not this question in particular. So first of all, look back in time. This with 64 intervals, blah, 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 you have something to the power of -16. Does that raise any warning bells to anybody? Should. Back to work. Why is 1e minus 16 a problem? Effectively, that is double precision 0. Anything below 1e minus 16 falls under round off. You get truncation error. It drops it. If you wanted to use something like quad precision, you could, and then you could continue tracking this down. I'm not actually sure where quad precision gets down to. Very few codes use quad precision because there's very few cases where that's actually necessary. But you can, if you were really keen, you could build your own package that would use quad precision. I'm sure SciPy and NumPy have quad precision variants. Any questions on Richardson or Romberg? Okay. We covered the engineering approach. We covered the physicist approach. And then Gauss comes in, and there's an expression I heard a while ago in corporate management called he seagulls it. Anybody ever heard of this? Somebody seagulling a problem? He flies, right? Seagulls fly in, they crap all over the place, and then they fly out. Gauss comes in, and he's just like, nah, let's do it like Gauss. right? Like, mind-blowing. Notice, up until this point, we've been doing various techniques. All these techniques have something in common, right? They're all approximating the integral as some sum of, well, here, I'll just show you this guy, right? So in the Newton-Cotes, if you look at the table, all these guys are always the integral is some constant, some weights, times the function evaluated at certain points, right? That's for the subdomain, the intervals. This is for the global one. This gets a bit more complicated. This, like, you wouldn't normally integrate our program in something like this. Usually you do some kind of recursive thing. Same thing with the Romberg rule. Again, you have that the integral is some weighted fraction of. Okay, it doesn't show it explicitly. It comes out to some weighted fraction of the function evaluated at certain points. Okay. Previously, up until this point, we were given the sampling points. We were told that this was a structured mesh. We measured it at time 0, time 1, time 2, time 3, whatever you want, right? And when you do that, you get something that goes like this. The integral is some constant times f at x0, c1 times f at x1, da-da-da-da-da-da. C's are constants that depend on the algorithm, right? And xi's, your sampling frequencies, are evenly spaced. And then what you do is you combine this and you kind of mix and match to get better answers. Gauss comes along and he says, what if we can choose our sampling points? If we can, then we can find magic points, which we're going to call Gauss points, for which the error magically cancels itself. And we don't even need to do that, which is super cool. It does require either a callable function, right? Because you're going to have to evaluate your function at certain points. Spoiler alert, the points are actually very well characterized. You can find them exactly where you want them. Either we would need the ability to call the function at those points, or we would have to engineer our entire framework to give us those function values at that point. That is exactly how the finite element method works. Gaussian quadrature is the single underpinning of the finite element method, which we're covering in, what, 2 weeks' time. Lightly. Okay, here's the magic. Nothing up my sleeve. We're going to propose a formula for the integral of some function f of x in the range -1 to 1. Okay, -1 to 1 is the convention through which everything else is derived. If you have something that is not -1 to 1, we just transform it into -1 to 1, right? Simple coordinate transformation. It gets a lot more general than that. You know, stay seated for this part. Okay, so you've got your integral. You've got the integral -1 to 1 of your function, and we're going to say that it's equal to c0 times the function evaluated at x0 plus c1 times the function evaluated at x1. And now we have 4 unknowns. We have our constants, c0, c1, x0, and x1. Since we have 4 unknowns, we need 4 pieces of information. Where do we get that? Let's require that this method will give us the exact answer for up to cubic polynomials. We're just going to impose that. Okay? Now, we can use this framework. If you remember, I didn't touch on this so much. I kind of alluded to it. A general polynomial of the form function spaces, linear function spaces. Not even 9 o'clock and we're talking about linear function spaces. Good. All right. You've got f of x, which is equal to something plus something else x plus something x squared plus something something x cubed. All these somethings are constants, right? What you can do is, and we did this when we were talking about fitting polynomials, you can express this guy, this is a cubic, right? in terms of your function space, which are your monomials, right? What the hell does that mean? It means that you can have some function of x to the 0 plus x to the 1 plus x to the 2, can't write a 2, right? And then you have to sum up these monomials. This is the linear function space part. You sum up the monomials until you get to the polynomial. Don't worry about that. What it means practically is that we can apply this to 4 functions. Function number 1 is going to be f of x is equal to, why is this x now? Yeah, x to the power of 0. Okay, so our first monomial is a 0th order monomial, which is x to the power of 0. X to the power of 0 is always 1, right? By convention. You plop that in here, right? This is your equation, and you compare that to the exact integral. Integral -1 to 1 of the number 1 is very simply 2. Okay, so this is our first line of information. Now we repeat the procedure with your function x to the power of 1. That's our first order monomial. You plop that in there, right? C0, x0, blah, blah. And you can integrate this exactly, and it comes out to 0. Why 0? Because you have a symmetric integral, right? You've got -1 to 1. You've got an odd function here, so it just cancels out. You do that again for your second order monomial, x squared. Plop that in here. This integrates exactly to 2/3. You do this again, but you don't have to worry about it because it's an odd function and you've got a symmetric interval. What you have, C0 plus C1 is equal to 2. C0 x0 plus C1 x1 is equal to 0. C0 x0 squared, blah, 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 is equal to 2/3. Yada, yada, yada. It is a nonlinear root finding problem, which you can actually solve exactly in all cases. When you do, this becomes your solution. C0 is 1, C0 is 1, C1 is 1, x0 -1 over root 3, x0 and x1 is the opposite sign. These are called your Gauss points. What this means, and this is the surprising part, right? I love when math like pulls out these surprises, right? The integral for a cubic polynomial, which has terms up to x cubed, is exactly the sum of that function evaluated at these 2 points and nothing else. Always. Always, always, always. Which is surprising, right? Like all you need to do is find the function at 2 points and you can calculate the integral exactly up to a third degree polynomial. Sure enough, the math checks out. Now that Gauss, maybe Gauss made a mistake. So Mike Wellen plots it into NumPy and double checks his work. And yes, it does work exactly. Right? Error 0, 0, 0. Again, finite precision. Is this surprising to anybody? Surprising to me that this thing actually works. Okay. Transforming it to an arbitrary domain. And then I'm going to hint at how this gets into finite element method. This is not a course on finite element method. There are courses on finite element method. So we're going to do like the super light, 10,000 foot view of this stuff. But enough, honestly, to navigate you around something like COMSOL, having done it for a separate course. Okay. The preceding derivation assumed -1 to 1. In order to apply it to an arbitrary domain, what we're going to have to do is we're going to have to transform that into the range -1 to 1. Here's the math. I'm not going to go through this. I'm going to be skipping a whole bunch of math here. It's all here. Feel free to check my numbers if you want. Right? What this ends up happening, and you can follow through the implementation here. Whatever your integration interval is, the first thing you do is to transform that to -1 to 1, and then you apply Gaussian quadrature, and out pops your answer. And you have to scale the area a little bit because you've done this this stretching of the domain. Did anybody use in COMSOL Lagrange elements of an order anything other than 2. Most of you guys wouldn't have even seen that option. Default in COMSOL is called Lagrangian elements of order 2. That order relates to the degree of Gauss points, the number of Gauss points that you're using. Gauss points, you could use more than 2, right? If you're using 2, you end up getting an order 4 accurate solution. Why order 4? Because you're assuming a quadratic. The quadratic part is exactly integrated, therefore your error is whatever's left over. If you wanted to use more points, right, you could get more information, but now you have, well, these are your coefficients, these are your C's, and these are your Gauss points, right? But now you're 6th order accurate. If you wanted to use more, then you could get another degree of accuracy. Now you've got 4 points. The notation is a bit tricky here, right? Because you've got 2 plus minus embedded in here. But now you get like an 8th order accurate answer. It's really cool. The actual error analysis is messy. And it is messy because we are no longer requiring evenly spaced data. Actually, we're explicitly requiring unevenly spaced data, according to this template. Here it is anyway. It generalizes pretty trivially to ND, almost. The idea that you could do a double integral is, and we talked about this with integration with, I think with Newton-Cotes, the ND extension is pretty simple because all you're doing is you're integrating over one dimension and then you're integrating that over another dimension. The exact same thing works out. However, the case of, there's a lot of math here. What becomes a bit more complicated is the transformation that you need to get back to the template. What do I mean by that? The original Gauss point derivation was for an integral, right? You've got A and you've got B. And what we're going to do is we're going to transform that to something from -1 to 1, right? And we're going to calculate it kind of on this, and then we're going to project it back onto that. In multiple dimensions, right? The easiest way that we can do that is by thinking about it like a square. So we've got our unit square down here. Now this guy is ABCD, right? This should be a square. Use your imagination. When you do that, you can identify your Gauss points, which is fine. But now you're going to take your square and you're going to contort it. And you're going to skew it. And you're going to make it look something like this. The transformation of this back to your unit square is not hard. It's cumbersome. Right? This is really where computers shine, because you set it and forget it and you just make the algorithm. What algorithm? It's all here. Knock yourself out if you really want. Some of you with COMSOL might have encountered quadrilateral elements. Typically, they're triangular, but quadrilateral are also powerful in a lot of cases. What is happening there is when you do a mesh, and if, say this is your boundary and you ask for quads, it's going to do something like that. But then it still has to be kind of spaced, right? Okay, but that would be a hanging note. So, anybody ever see something like that? COMSOL when you're meshing it. We didn't spend so much time on meshes, so don't worry about it too much. Every single one of these squares has to be transformed back to the unit one, right? In order to apply the Gauss processes, or the Gauss points. The way it actually works is that you do that you find the Gauss points for the unit, and then you transform those to those, but it's just a matter of algorithm. They're conceptually the same. Make sense so far? There's one more big old wrench that's going to be thrown into it, because one possible transformation that you might do for this guy is this nasty one. And you've just made one of these guys degenerate, even to the point where this actually just becomes a triangle, right? Quads are convenient, but they are not the, I think the term is simplex, right? They are not the fundamental shape in 3 dimensions, because there are degenerate geometries that can be made by taking one of those edge lengths to 0, which is why in COMSOL, if you just hit that magic mesh button, you're going to get a triangular mesh, because there is no the degeneracy of a triangle is a lower dimension object. Does that make sense? You could take a triangle, you could shrink one of the sides, but now you have a line. It's no longer a two-dimensional object. If you have a square, you shrink one of the sides to 0, you get a triangle. It's still 2D. I think that term is simplex, but don't quote me on that one. Yeah, tessellation, by the way, is a process of that mapping and that kind of subdivision into these triangles. This map gets a bit intense. You have to transform it into, what do they call it? The area coordinates. Blah, 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 blah. You work out, here's some tensor notation. And sure enough, you get some magic answers at the other side. I'm not going to go through this one at all, guys. There are pages, there are textbooks devoted to finite element analysis. This is basically the first few chapters. There are websites called the Periodic Table of Finite Elements that'll take you through all the different variations of that, and that gets even more complicated. Probably grad or above grad, actually, even for that stuff. Okay, what I do want to point out, though, is you can still prescribe different types of Gauss point applications of this. So if you were to say a first order Gaussian quadrature, now, right, we did, the one that we described in class was 2-point. We had C0 times F at X0 plus C1 times F at X1, right? You don't actually need that. You could actually just get away with C0 times F0. It's kind of like a trivial case, but that would be your linear elements here, okay? So on your triangle here, you have a single data point, no problem. For the quadratic elements, it turns out that your data points are actually attached to the side, which has implications for continuity between the mesh elements, right? And for cubic, you kind of subdivide this according to your Gaussian point, your Gauss point derivations. So all I got with the integration. I'm just going to wrap that up. Newton-Cotes, the engineering approximation kind of always works. We can do better under special cases if the mesh points are a factor of 2, if you have a callable function that you can evaluate ad nauseum. If you have a callable function, though, honestly consider using Gauss points, because Gauss points are kind of the most bang for your buck, right? You're going to get a 4th order accurate algorithm with only 2 function calls. When you would want to do that is something like if your function is an entire finite element code, right? And you're waiting for this thing to solve. And every single call takes like an hour or something like that. It's all over optimization of these finite element systems. That's like part of what COMSOL is doing when it's running the optimizers on it. But at the same time, Gaussian quadrature is what's underpinning the finite element method. Okay, we've got like 12 minutes left. Any questions on this or midterm material? I will check the Teams message too. Nobody? You're free to go if you don't have any questions. But I'll wrap up the lecture here. If there are any questions, feel free to shout them out. If you have somewhere better to be or you need coffee on the way or something, go for it.
Last lecture we talked about how to get
trapezoid.
Yeah. How to get 4-inch square.
Sorry, how do you get it?
Yeah.
Oh, okay. You can look at, so there are 2 ways to do it. You can either look at you can do it the proper way, right? Which is you're going to have to do the Taylor expansions. It's here, right? So what you're going to have to do is you're going to have to do the Taylor expansions around both of these points, the beginning of your interval and the end. Then you're going to take the average of it. You're just going to apply that formula, and it's going to fall out like this. right? And then you have to do that again, and it gets a bit more intense. But what you end up getting is that the trapezoid rule on the interval is order h cubed. But because the smaller your interval is, the more of them you need to add them all up. And how many you're going to have is going to be proportional to your step size. If you have an interval that is 10 units long and your step size is going to be 1 unit, you're going to have 10 of them. Yeah, you end up dividing through by a factor of h, right? So your h cubed becomes h squared.
But the Taylor expansion gets it.
Yeah, so the Taylor expansion will get it for you on the interval.
Yeah.
So yeah. Right, so there's on each one of these guys, this guy is going to be h cubed, right? This guy is going to be order h cubed. This guy is going to be order h cubed. Right? When you're adding up all of these guys, that error is going to accumulate.
Yeah.
And the number of intervals that you have, the number that you're going to have to add over, is whatever that interval is. Let's say it's 10. Okay. 0 to 10 with h is equal to 2. Right? Number is, see you later, 10 divided by 2, right? But more generally, it's whatever that is over your step size. Okay, so the total error becomes for the whole thing is order for the intervals times the number of those intervals, which is something over h.
Okay.
That h squares. That h cancels. And what you're left with is order h squared.
Yeah.
Yeah. Everybody's confident. That's good. I see big answers coming out of this midterm, guys. Good. See ya. Howdy.